friends, in this video we are going to study the Carey-Foster slide wire bridge method, which is used for the measurement of medium resistances. Medium resistances are those resistances which are in the range of 1 ohm to 100 kilo ohms. So the resistances which are in this range, they are categorized as medium resistances. Here we are studying the Carey-Foster slide wire bridge method, which is used for the measurement of such medium resistances. So let us start with our topic. The Carey-Foster slide wire bridge is used for the measurement of resistances which are nearly equal in their values. Okay. This Carey-Foster slide wire bridge, it is just like the Wheatstone bridge, in which we are having the 4 arms, and in the 4 arms we have the 4 resistances, and the bridge, that is Wheatstone bridge, is said to be balanced when the galvanometer shows null deflection, and when the bridge is balanced, the ratio of the resistance arms, that is P by Q, is equals to R by S. So this Carey-Foster slide wire bridge, it is also a modification of the Wheatstone bridge. It works on the same principle of the null deflection. So let us first see the circuit diagram for this Carey-Foster slide wire bridge. So this is the circuit diagram for the Carey-Foster slide wire bridge. You can see that this is similar to the Wheatstone bridge, in which we have the 4 arms, and in the 4 arms we have the 4 resistances P, Q, R and S. P, Q, S, these are the known resistances. S is the standard resistance and R is the unknown resistance. Now in between it we have a slide wire, and on this slide wire we have the sliding contact which is moving over it. Now when the galvanometer, it is showing the null deflection, it means that the voltage drop across this EAB and EAD, it is equal, or we can say that no current is flowing through the galvanometer. So at that condition, the ratio of these resistances, that is P by Q, is equal to R by S. Now here in between this we have this this slide wire is connected. That is why in the name of this bridge we have the slide wire bridge. Okay, Carey-Foster is the scientist who developed this. Now this length of this slide wire is L. Okay, and on this sliding contact is moved. Now suppose at this D position we are getting the null deflection in the galvanometer. So the ratio of the arms, like suppose that we are getting the deflection as this point, and the length of the slide wire is L1 at this point. Now R is the resistance per unit length of this slide wire. So L1 multiplied with this resistance resistance value will be added up in this unknown resistance, and then the ratio of the four resistances calculated. Now again we are interchanging these two resistances, like at the position of R we are connecting S, and at S we are connecting R. Again we are finding out the deflection. Suppose at length L2 we are finding that deflection. Again we will calculate the ratio of the four resistances. From the two equations or from the two connections, we will obtain the value of the unknown resistance. So this is the working of the Carey-Foster slide wire bridge. Let us again see this. So as we have seen that the working principle of this Carey-Foster slide wire bridge and the Wheatstone bridge, they are same. They both, these bridges, they are based on the null deflection method. So the working principle of Wheatstone bridge is what? The bridge is going to be balanced when the ratio of the resistances is equal, or we can say the galvanometer will give us null deflection when no current is flowing through it. So here also the potential fall is directly proportional to the length of the wire, and the potential fall is nearly equal to the potential fall across the resistance which is connected in parallel to the battery. Okay, so here in this Carey-Foster slide wire bridge, we have a slide wire which is of length L, and this slide wire is connected between the R and the S. Now in the bridge circuit you can see that the P and Q, they are adjusted such that the resistance, the ratio of the resistance P and Q and R and S, it is nearly equal, and this is achieved by sliding the contact on the slide wire. So here we are having a slide wire which is of length L. Okay, sliding contact is moved over the wire. Now when the connection is like R, P, Q, R and S, and then when the sliding contact is moved, let us suppose that L1 is the distance of the sliding contact from the left hand side. From the left hand side, if we are measuring, suppose at the length L1, we are getting the null deflection in the galvanometer. Okay. So let L1 be the distance of the slide wire from the left hand side, and when we have connected, like if the connection of the bridge was like P, Q, R and S, and at that time we have seen the null deflection in the galvanometer. So L1 is the distance from the left hand side. Okay, now R is the resistance per unit length, okay, of this slide wire, and the total length of the slide wire is capital L. Okay, so if we want to find out the resistance of this part which is having the length L1, so it will be L1 multiplied with R. Okay, that will be the resistance of this part. Now when we have seen the galvanometer, in the galvanometer we have got the null deflection. It means that the ratio of P by Q upon R plus this much part, that is L1R, and here S, in this S we know that the total length is capital L, so L1 is added in R, so the remaining part is what? L minus L1. And when we multiplied this with this resistance per unit length, so this much part of the resistance is added in the standard resistance. So for this first case, when the connections are like P, Q, R and S, in that case, if we write the balance equation, so for first balance, the equation will be like P upon Q equals to R plus L1R, means L1R part will be added in the unknown resistance. And here we are having the standard resistance. So in that standard resistance, L, that is total length of the slide wire, minus L1, that is the distance where we have got the null deflection, multiplied with R. Okay, so this is the balance equation for the first case. Now in the second case, the resistance R and the standard resistance S, they are interchanged. Means where R is connected, at that position S will be connected, and the position at where S is connected, at that R will be connected. So the positions of R and S are interchanged for the second case. Now in the second case, suppose again we want to find the null deflection in the galvanometer. We are sliding the contact over this slide wire, and suppose that at length L2 from the left hand side we have got the null in the null condition in the galvanometer. Okay, now this L2 length, it will be added in this standard resistance, and the remaining length will be L minus L2. That will be multiplied with the resistance per unit length, and that will be added in the unknown resistance. So for the second case, the resistance R and S are interchanged. So now the balance equation will be, again P by Q is equals to S plus L2R, okay, upon R plus L minus L2R. Okay, this much part multiplied with the resistance per unit length, so length and length, they will be cancelled, and this term will have the unit of a resistance only. So that will be the resistance of that part, that additional part, and it will be added in the respective resistances. So we have got two equations. One equation when resistance are connected like P, Q, R and S, and second case when the resistance are connected like P, Q, S and R. Now from these two equations we know that the left hand side of both the equations is same. They are having the ratio P by Q. So we are going to equate these two equations. Okay. So by equating we will get we have equated the first and the second equation. Now adding 1 to both the sides. sorry, this is minus L1 R plus 1. And here on the right hand side also we are adding 1. Just solve this, multiply this. Now multiply this inside the bracket. Okay, so we will get R plus L1R plus S plus LR minus L1R. L1R and L1R having opposite signs plus and minus, so they will be cancelled. Here L2R will be cancelled. So what we have got, S plus R plus LR upon here also S plus R plus LR upon R plus L minus L2 R. The numerator terms on both the side, left hand and the right hand side, they are same, so they will be cancelled. So we are left with 1 upon S plus L minus L1R equals to 1 upon R plus L minus L2R. Let us solve this. So what we have done, we have cross multiplied these terms. So we have got R plus LR minus L2R equals to S plus LR minus L1R. Now here also we are having plus LR, here also we are having plus LR. When we will bring it to the left hand side, it will be cancelled. Okay, now here bringing this L1R to this side and bringing this R to the right hand side. So what we will get, S minus R is equals to L1 minus L2 multiplied with the R. Okay, so what we have got, that is the difference between the standard resistance and the unknown resistance is equal to the difference of the length, where we have got the null deflection in both the cases multiplied with the resistance per unit length. So in this way, if we got, because standard resistance we already know its value, L1 is the distance in the first case and L2 is the distance in second case. And R is the resistance per unit length. So we can find out this unknown resistance R with the help of all these variables. Okay, we are going to put the value for all these variables in this formula and we can easily find out the unknown resistance using the Carey-Foster slide wire bridge. So here We have studied that the Carey-Foster slide wire bridge, it is used for the measurement of comparison of nearly equal resistances. If suppose the standard resistance and the R, they are nearly equal to each other, so we can easily find out through the difference the value of this unknown resistance. So in this video, we studied about the measurement of medium resistances using the Carey-Foster slide wire bridge. So I hope that this topic is clear to you. Thank you.